Introduction. So hello everyone, and welcome to our presentation entitled by Investigating Methods to Improve Language Model Integration for Attention-Based Encoder-Decoder ASR Models. And I'm Mohammad, a PhD student at RWTH Aachen University and also affiliated by Aptec. And this is a joint work with my colleagues Aleksandr, Glushko, Wilfried, Michel, Zeyer, Ralf, Schlüter, and Hermann. So to begin with, attention encoder-decoder models benefit from external language model integration. So usually we have much more monolingual text data, and we train an external language model of this. And when we integrate this with the ASR model, we get much more improvement. But the problem is that because of the structure of the attention model, we basically learn an implicit internal language model. So if you look at the architecture of the attention model, so we have the encoder that encodes the input into hidden states, and then this would be used by the attention mechanism in addition to the decoder state to generate the context vector, and then this is used by the decoder and in addition to the previous label in order to predict the output, the next output. And because of this label recurrency in the decoder, it acts somehow as an implicit language model. And in order to do a proper integration with an external language model, we need to consider this. So the question is how we can compute this internal language model probability to do prior correction during recognition in order to get better improvement. So now if we look at some equations, so during recognition, we would like to have the best word sequence that maximizes the posterior probability, right? So the probability of a word sequence given the acoustic features. We could define this posterior probability as a model combination of the ASR model. So the posterior probability in our case would be the attention model and the probability of the external language model with a scalar weight lambda1. But we could also now introduce the probability of the internal language model in order to do prior correction. And that's why we have a negative scale, because it's a prior correction, so it's a division by the probability of the internal language model. Now, the exact definition of the internal language model requires a summation over the whole acoustic space. And probably this summation is intractable, and therefore we need to think about ways in order to approximate this. And that's, in this work, so we propose different methods, novel methods, to estimate this internal language model directly from the model itself. We could also classify these internal language model estimation methods as model agnostic methods. So basically, estimation methods that are not part of the model itself. So example of this would be the density ratio method. This is a popular method also for internal language model approximation and also prior correction, where basically we train the language model externally only on the transcription data and then use this as an internal language model approximation. But there was recent work where they basically considered the model itself in order to estimate the internal language model. And these, we call them like model-specific methods. And the idea behind this is that we look what is the input representation in our model. So in our case, since we have an attention model, this would be the attention context vector. And we try to mask out this information and then let the decoder only consider label input. But the thing is, here we argue that this is not consistent with the training. So during training, the decoder still sees some encoder information. And probably masking out all the input representation is not a good idea. So in this work, we focus on model-specific estimation methods by replacing the attention context vector with either static vectors or even trained context vector with the aim of minimizing the perplexity of the internal language model. So this is the architecture we used. So it's attention encoder-decoder base model. So for the encoder, we use CNN on top, first layers, and then followed by MiniLSTM layers. And we have also time max pool layers in order to do time reduction. And yes, so the hidden state then we use by the attention to, in addition to the decoder, in addition to the decoder LSTM state in order to generate the context vector, and then this is used by the decoder in addition to the previous label in order to predict the next label. And so now we will focus on this part, so on the decoder, and we will focus mainly on how we can modify or change this original attention context vector in a way that we will get an estimate of the internal language model probability. So the first methods we looked at are static context vector estimation. So the idea is that we have a static vector, position independent, and this replaces the original context vector. And we could replace this by different ways. So the proposed approach was the zero vector. So simply you just have a vector with all zero elements. So this is what was proposed before. And so in this way, you mask out all the input representation. But since we thought like, okay, maybe using encoder bias would help and lead to more improvement, since this is more consistent with training, we considered two different approaches. One way is where we average all the encoder states over all training data and then dump this into one vector and then use this instead of the original vector. Or we could also average all the context vectors over training data and then use this instead of the original one. So here, as you see, so we have now a static vector. So instead of the original position-dependent vector, and then we use it, to get an estimate of the internal language model probability. But then we also thought, okay, what if we can train this attention context vector in a way that it minimizes the perplexity of the internal language model? So this probably would be a better approach, and that's why we thought about this approach. And the idea is we freeze all the parameters of the attention model. So you train the ASR model, then we freeze all the parameters, and then we add two trainable layers. So the first layer we called a MiniLSTM. It's simply one LSTM layer, and it's mini because it's only 50 hidden units. This is followed by a linear layer, which basically take the output of the MiniLSTM and project this into the dimension of the context vector. And this is, as you see, it's position independent, and this MiniLSTM only consider labels. And since the objective function is cross entropy, so we directly minimize the perplexity, and also this is trained only on transcription. And we don't have to train this for a lot of epochs, so it was enough to train only on a few epochs. And we will see later that this method achieved the best results. We also thought about a different direction is, what if we can also suppress the internal language model? So if we can weaken the effect of the internal language model, so maybe this will also help, or how this compare to the previous methods I explained. And one way we can do is that we can use a limited context decoder. So instead of having a recurrent decoder, LSTM decoder, we could just have a decoder with just limited context. So basically replacing the LSTM layer with feed-forward layers and consider some context. So we hope we get a less effective internal language model by this. Another way is to train the ASR model with a language model, so via sequence training or local log-linear combination. And this way we hope that the ASR model focuses more on the acoustic model part and leave the language modeling part for the language model component. So now for the results, we evaluated our results first on the switchboard 300-hour task, this conversational telephony speech, and we can observe that. Okay, so using our ILM methods, or in general, subtracting internal language model outperforms the standard approach like shallow fusion, which is simply just a log-linear combination with the external language model. And with our best method, which is the MiniLSTM, which is a trained context vector, we can achieve a 6% relative improvement in terms of forward rate compared to shallow fusion. And we can also here observe that using, so these methods uses encoder bias, so the average instead of 0, and we can see that they also better than using the 0 approach. And in this case, also even density ratio was better than the 0 approach. We also evaluate our methods on the Libre speech, 960 hour, and here we also observed consistent results. And we even got more improvement. So we achieved 15%, 16% relative improvement in terms of order rate compared to shallow fusion, which is the most standard approach, or popular approach used to integrate external language model. And also, again, with the trained context vector or the MiniLSTM approach. And also, if you compare also, in general, ILM methods outperform like shallow fusion. Here we also tried the ILM suppression by training the ASR with a language model, and we can see that we can get good improvement, also comparable to some of the internal language model methods. We also were interested to do a cross-domain evaluation. So what we did is that we took the ASR model trained on Libre speech, and we evaluated this on the Tadelium version 2 dev and test data sets. So again, we can see, so density ratio would be here the popular approach used when you do prior correction of different domain, out of domain, target data. And we can observe that our method, the MiniLSTM, or the trained context vector, also outperform density ratio in this case. For the limited context decoder results, it turns out still even if you have a limited context decoder, internal language model subtraction still helped. So here we can see improvement when you do ILM subtraction. And in this case here, we use a one-layer feed-forward decoder with context size 3. And we also observe that average-based static methods perform better in this case. And here we actually achieve comparable results to even a recurrent decoder. So in conclusion, subtracting the internal language model during conditioning gives significant improvement in terms of forward rate. We propose a novel method to train the attention context vector for ILM estimation, which outperform other methods. And we achieve 6% relative improvement on switchboard 300-hour task, as well as 15% and 16% relative improvement on library speech. And we also trained limited context decoder attention model, where we can achieve actually comparable results to a recurrent decoder on the switchboard 300-hour task. And this work shows the importance of considering ILM subtraction somehow kind of a standard approach that should be used in order to achieve better results. Thank you for your attention, and I'm happy to answer any question.
Thank you. We have lots of time for questions, actually. Anything? Okay, there are a couple in the floor there.
So, thanks. Very nice work. So you do it to replace the language model in the decoder. Have you tried to train it on more data using your MiniLSTM trick?
So you mean in addition to the transcription data?
Yes, yes.
No, I didn't try this.
So then you don't have the external language model. You just have the model which is possibly
we still
better.
have that. We still have the external language model. So yeah, here. So we still include the external language model probability. But when we estimate the internal language model, the text data we use is only the transcription data.
Yes, so the question was, have you tried to make the internal language model better? Rather than replace it, make it better by training on more data.
But the question is, okay, I mean, but usually the model only sees transcription data. Mm-hmm. So the intuition was here, if you want to estimate the internal language model, you would probably want to use the same data as what the model was trained on. Okay, but I mean, you could consider training on certain data, but I have no idea what would be the effect on this. Mm-hmm. But to be more consistent, this would be training on the transcription data only.
Thank you.
Thanks for the nice talk. Really interesting. I have two questions. So the first one would be you're actually modifying the attention context vector, right?
Yes.
So do you think there's any kind of influence of the internal language model also in the encoder part? Because there you look mostly on the decoder of the network, right? So do you think there's some kind of internal language model also in the encoder?
I mean, maybe this is... Okay, so using also the average of encoded state helped. So maybe some information from the encoder also was useful, because in the result we saw okay, so also considering, sorry, yeah. So also considering average methods, or when using encoder bias, it also helped, using the compared to zero approach, where you mask out all the input representation from the encoder. So this can be useful, yeah.
Okay. Yeah. Second question would be: do you think this? So this was basically a LSTM-based encoder-decoder model. Have you looked if this also applies to transformer models?
I did. Yeah, we did this. This is only related to the attention context vector, right? So, any kind of decoder you can do this. So in this way, you would do the same, just replace the attention context vector and feed this the static or trained one to the transformer decoder, and this will work. Yeah. Okay,
yeah, because I think for transformer you usually have some multi-head.
Yes, that's true. And I tried also if you have one or if you have multiple, so you have let's say 6-layer transformer decoder, then you end up with 6-layer, let's say MiniLSTM layers, or you train 6 different. You learn different 6 different attention context vectors. It was the same, so one was enough. Yeah.
Nice.
So we have also written questions from the virtual attendees. First question from Petr Zizin is: why would you consider subtracting the ILM? Is it because we assume that the external language model trained on big text only, on a big text only corpus should perform better?
So there's 2 reasons. So one is it's a better biased interpretation, so similar to what we do in hybrid. And second, for sure, when you have out of domain, you need to do prior correction. So yeah.
Yeah, thank you. Still no question? I will continue then. question from Jesus Andreas Ferrer. How does this compare to the internal language model estimation or HAT approach?
HAT approach, exactly. So, I mean, this is an attention model. The HAT approach actually considers the zero approach. But we cannot directly compare because, I mean, the decoder, how the prior learned by the transducer decoder is different from attention. So probably, maybe, so the zero approach was here a bad estimation, right? We can see from the results, so on libre speech or like on switchboard. So it was worse with the zero approach. Yes.
Okay.
So we have one question from the hall.
So hi, thank you for the presentation. I wanted to ask which framework did you use for neural network implementation, and is the code base somewhere available online?
Yes, the code is available, also the configs to run the experiment and to produce the results, and we use return, so our framework in RWTH Aachen University, public tool. Yeah.
Okay, thank you.
Welcome.
We still have some time, and I think we still have some online questions.
Okay. Rui Zhao is asking if the optimal lambdas be the same or similar for different tasks and ILM configurations.
It will be different. So this also depends how much data you have. Like in libre speech, since like we know like we have 800 million, I think, for that Sterling language model. So yeah, the weights were different. I remember for libre speech we had also in the paper they are written. We have 0.68 for the external language model and 0.40 something for the internal language model. For switchboard it was a bit smaller. Because also we don't have a lot of transcription data, 24 million external language models, so the weights will be different. And we tuned this using grid search.
Okay. I have.
Sorry, go on.
If no one has any other question, I have one personal question.
Yeah.
Well, I have just one question from my person. Did you, as a baseline or naive approach, did you try to use count-based language models at the output and subtract those? Or just imagine you would train count-based language model or even RNN language model on the training data and subtract that instead of estimating the ILM using your method.
So basically density ratio approach.
Well, you would do, essentially you would reweight the output by the difference between the training language model and your external language model.
Yes, but in this way, so you think you train a different model?
It's similar, it's just more naive approach than you are doing. You are doing much more elaborate and careful job.
Yes.
I'm asking what would be the difference if you try to evaluate what is the efficacy of your approach compared to these naive approaches.
I think it's because it's a model-specific approach. So it considers the model itself instead of, so that's what I would say, which probably intuitively it would be better.
Okay.
When you consider the model itself, yeah.
That brings us nicely to the end of the slot. So perhaps we could finish by thanking the speaker again.
Thanks, everyone.